5-3. I'm going to jump down to our real quick spot here. Like I said, going to go through this rational zero theorem. Okay, don't worry about it too much. Listen, like I said, ugly definition. All it means is this, remember? You're looking for zeros. Okay, first off, right now, you're trying to find every factor, okay, between a to the sub-zero and a to the n. Look at our definition. Here's a to the 0. That's your constant. Okay? A to the n, that's going to be your leading coefficient. We need all of the factors of both. Remember when we were doing that P over Q? Notice what it says. P is a factor of here. So that's going to be your P terms. Okay? This is going to be your Q. And so then it says any rational zero must be of the form P over Q. Okay? So you're making a whole bunch of fractions. Granted, some of them won't be fractions because you're always going to, in Q, you're always going to have a 1 as a factor. Because think about it, if I gave you 13, well, 1 and 13, there's your factors. That's it. But still, you still got that 1. Okay? That can help you out a little bit. Let's look at one really quick. We're going to go back over just how to do it, and then we're going to jump back into our examples. So I don't want you to get lost in this because it comes back up all the time now. Okay? We don't have to worry about that. I'll explain in a second. So notice on this one right here, we're not going to factor it just yet. Using the rational zero theorem. Okay. All we're doing right now is trying to find zeros. Okay, there's a reason I'm hanging out in 5-3 for a little bit. Remember, this was my Q. We did this one yesterday. No, sorry. This is my P. That is my Q. We're going to come in here, find all the factors of P and all the factors of Q. Okay? What's nice is looking at Q, how many factors are there that leading coefficient? Yeah, just a 1. That's super sweet. Okay? But then we look at all the factors of the other one, and you've got 1, 2, 4, 8, 16, 32, and 64. And I'm going through that very quickly because we did this part yesterday, but I'm just trying to remind you how we did it, okay? You have to go in and find all those factors. But you're technically not done yet. This one you are. This is what's nice about this one. Your Q only has one factor of 1. But remember, if there was another number here, now you got to start taking every single number here and dividing it by, and so you're going to add on a whole bunch of fractions off the back end of that guy. That's why it's called the rational root theorem. Now, what these numbers are, hear me carefully again. I'm going to reiterate this a lot. These are all of the possible zeros of that cubic, of that polynomial. Is it all of them? No. I guarantee you this. With 3, one of them is going to work. One of them will, for sure. You'll see that as proven fact when we get to 5-4. Okay? But remember what I said. You could have one real, but what could you also have 2 of? Always 2 of. Always a pair.
Complex numbers.
Complex numbers. Complex numbers, we call them conjugate pairs. Remember when you solve them, you always get that plus or minus. That's why they always come in pairs. Okay? So you got it. Now remember, what's the problem with this? This is not all of them, is it? What am I missing?
Plus or minus.
Plus or minus. You're going to have plus or minus on both of these. Okay? Which takes a very small list where you go, dude, that's an easy list. And then double it. Okay? We do that. Now, remember, I'm making this look really, really easy because I don't have time to sit here and go, all right, let's start testing numbers for the next 10 minutes and all this stuff. I already know one of the factors, okay? One of the factors for this one was a 4. Hear me out. Once again, I said this yesterday, I'm going to say it again today. Your goal is to take the polynomial. This one right here, let's be honest. Could you factor this one right now in its form right now? Think about it. I want you to think really hard. How many terms?
Grouping?
Exactly, by grouping. You could factor by grouping. And you'd be done. Now, had there been a power of 4 and you had 5 terms, you're done. You can't do it. You're gonna see, and if this class was longer, even by just like 30 minutes, there is a wonderful little history lesson that comes with this, like trying to find factors. It's actually really interesting. Because we know how to factor powers of 2, that's super easy. Powers of 3, we can kind of do grouping. After that, it gets like, there's no formulas anymore. Okay, they just get too hard. So you're trying to get these down from a high power, high degree, low enough that you can use some sort of factoring technique you already know. Quadratic formula, factor by grouping, AC method, something, you can get it down to there. Okay? You could even keep going. I mean, in essence, you could take this all the way down to a degree of 1 and just get it all the way factored down to it just, there you go. That would take a really long time. Don't know why you do it. Notice on this one, I'm going to tell you right now that 4 is a 0. How do I know? How do I know 4 is a 0? What do I have to do? When I'm checking numbers, how do I know 4 is a 0?
Equals to 0.
Exactly. I plug it back in, right? That's your check. That's the part that takes the longest, is the checking. Is you take that -1, you plug it in and go, that didn't work. Take the 1, that didn't work. Take the 2, that didn't work. Finally, you get to 3 and go, there's my 0. So when x equals 4, I actually have what as a factor? Remember? Okay, 4 back over, you got x equals 4, but you actually have x minus 4. Remember? Everybody good with that? Think about it. You're factoring. Okay, so I plug in a 4. We're going to use synthetic division to bring this down. We take the 4, then we write all our coefficients, making sure that if we do not have an x value, like an x to the power 2 or something, we put what there? 0. Always replace it with a 0. Placeholder. Okay. For this one, obviously, I've got 1, -4, 16, -64. Draw my line. I get a freebie right there of a 1. Diagonally, we do what? Multiply. We do what vertically? Add. So 1 times 4 is 4. That's going to turn into a 0. 0 times 4 is 0. Bring down the 16. 16 times 4 is 64. And how do I know for a fact this is a factor? What do I have to see? A 0 right there. That means that this 4 is a factor. It is a 0 of that. That means x minus 4 is a factor. What does that mean? Take x minus 4 and do, remember that long division I taught y'all? In the last chapter in 5.2, you could divide x minus 4, or divide this divided by x minus 4, and you get a remainder of 0 because it's a factor of it. Okay? Good? Okay. Notice now we rewrite. Now I have, well, this is, we are lowering everything by a power. So this is going to turn into x squared. I do not have an x, do I? It went to 0. My constant has now turned into a what? 16. And then I don't have anything over here. So I have x squared plus 16. Notice, I've now factored it. I have x minus 4. How do I know that? Because of that guy right there. I found that 4. I would suggest, if you're doing anything of a higher power, now notice what I could do here. I could come in here and write this as x squared plus 16. And if I wanted to, you could probably go in there and factor that more if you want to. Why? Okay. How many real zeros do I have though? 1. Because what's going to happen over here? When you solve for 0, what's happening there? You're going to get a conjugate pair. You're going to get a complex number because that's going to come over and make a negative 16. Okay, what did I tell you when I said I started dealing with a power of 3? What am I guaranteed to at least get one of? I'm guaranteed one real number. Now, could I have gotten 2 negative numbers and then be real numbers? Yeah, could have. Did I? No. Okay, I got 2 complex. But what they do is they add up to what? 2 and 1 equals 3. Okay, so notice if you finish this off, you would get x is equal to 4. This one over here, can anybody tell what that's going to be? X is equal to positive or negative what? How about 4i? Don't forget, pull that negative out, make it an I, take the square root of 16, which is a 4, and there you go. And then notice we have 1, 2, 3 answers. You're going to always get 3 answers. Not all of them real sometimes, but it's because it's power of 3. Good way to check yourself, isn't it? Good on that one? Okay. Now remember, I gave you some rules, not rules, some help. I said, hey, what if you want to use Descartes' rule of signs? Okay, Descartes' rule of signs literally says, hey, this is how many real numbers you could have. This is how many negative numbers you could have. Possibly. Doesn't guarantee. Descartes' rule of signs does not tell us specifically. It will. Okay, if you get a 1, if you get a 1 in either one, the positive or negative, you're guaranteed that one. But remember, anything above 1, you got to take that largest number and then start doing it by what? Subtracting how many numbers? Think about it. How many conjugates could you have? Those complex numbers, you could always have what? 2. So imagine it this way. I'm not doing it yet, but let's pretend I give you a polynomial and we do a change of signs, and on the top for the positives, okay, you get 3. Well, doesn't that also mean that there's how many other numbers out there? 2, 1, or 0, right? For the positive. But let's think about it. That's not possible. I couldn't get 2. Okay, I could only get 3 or 1. Bless you. Why is that? Because embedded in there could be what? 2 complex numbers sitting in there. And Descartes' rule of signs doesn't find those. It can't. It's like, I don't know if they're there. It's literally saying that I don't know. Now, had I just got a 1, can I subtract 2 from that? I mean, I could, but can you get negative answers? No. So if I get 1, I'm guaranteed. Oh, look, I guarantee I'm gonna have 1 real number. What's nice about that? Hear me out. Your goal is what? Factor enough, right? You got this long, long list of numbers. What if I give you one, the positive number you only got 1 of, all of a sudden you're guessing for a number and you get you guess one of the positives and you get it. How many of the positives are you gonna have now? 0. Done, right? So now all those pluses and minuses that you're gonna have to go through, you can get rid of all the pluses and go, I'm not gonna have, I can just worry about the negative numbers now. That's what Descartes' rule does. It kind of helps us narrow in our list a little bit and go, okay, well, I got rid of this. That kind of help out a little bit? Okay. Look at this one here. In fact, you know, we'll wait till we get down to a bottom whenever we do one of your homework questions. Then we'll do the whole thing all at once. We did bounding. I'm not going to go over that one too much. Like I said, if you want to really look at the bounding one, it's really good if you get, it's testing an upper and lower. Remember, if you get a really long list of numbers, it's saying, hey, man, test one of your positives. If you do your synthetic division on one of your positive numbers and then all your little numbers down below are positive, that number's a bound. That means there's no other number greater than that. So then you can go, oh, my list is it's at least going to go to here. Same thing with the negative, except you got to have what? Remember who can remember? Not all negatives, it's gotta do what? Remember they alternate, positive to negative, positive to negative. If they alternate, you found a lower bound. Do I use this a lot? Mm-mm. You don't even hear it really taught a lot. I want to teach it because you never know. Maybe you get a really big list, okay? And you want to go, I want to see if I can find it without looking it up on Quizlet or something like that, okay? Get a really big list. I'm going to use all these little tricks to see if I can't narrow in my list as much as possible. Because I don't want to be there for 3 hours looking through a list of 64 numbers. Let's see if I can't get that down to 10, okay? And then we've got the intermediate value theorem, which just simply states this, okay? Notice, assume that f of x is a polynomial with real coefficients, can't have complex numbers. A and B are real numbers, okay? A is less than B, so you always have to make sure that when you do your A, it's less than your B. You can't put in your B and then go backwards, okay? You can't do it that way. If f of A and f of B differ in sign, then there is at least one point C such that A is less than C is less than B, and f of C equals 0. That is, here's the explanation. At least 1 0 lies between A and B. It literally just said, look at the picture. F of A is basically my Y, right? F of B is what? Another Y. Notice my A is saying, I've got an A here, a B here. C is saying, hey, if this is a different sign than this, which you should look at this and go, these should be different signs. This is in the negative region. This is in the where? Positive region. If they change the signs, are you guaranteed a 0? Yes. Do you, why is that? Just tell me, just look at the picture. Why is that? To go from a negative to a positive, what has to happen to that line?
Cross the X.
It has to cross the X value. That's why you're guaranteed a 0 there. Okay? And vice versa. If your A is positive and your B is negative, then what's going to have to happen? It's going to come down. That's what it's saying. Okay? And then let's do that one. We did that one yesterday. Remember, all we do is plug in, right? Plug in 2, plug in 3, look at your numbers. These both became positive. Since these were positive, was I guaranteed a 0? No. Does it mean there's not a 0? No. You could have complexes. Okay? But it's saying real numbers, there's no 0 there. Okay? Help you out a little bit? Trying to decide if that's the harder one or is. Let's do that one. That is the last one. Okay, let's do this one. The reason I'm doing this one is my A sub 0. Notice it's a 3. I am giving you some easy numbers on this one. Okay. First off, we have to look. This one is a little bit tricky. Okay. Look at it very carefully. Do it however you want, but this is what I always do with these because it can get so confusing. Okay. First off, let me change it back to red. Whoever's coming here using green is weird. Okay. That's my P. That's my Q. And specifically, it's the leading coefficient that's your Q. We don't worry about that X to the 4th. We just know that's my leading, that's my degree. Okay. Can you see the importance of making sure you're putting this in descending order, making sure you're putting everything in order first? Okay. They will try to trick you and put these out of order. Okay. Then you do all this work and realize, ah, crap. Okay. Come in here very carefully. We're going to look at P. Let's try to find all our factors of P, which is pretty easy because it's a prime number. What are my factors? Yeah. 1 and 3. Well, how about Q?
1, 2, 4.
Exactly. 1, 2, and 4. Okay, so now I've got to make a list of zeros. Okay, and I stole Hawk's. I like how Hawks does it. I like how they do their grouping. I used to do it. Every number had a plus or minus in front of it. And I saw how Hawks did one time. I was like, oh, I like that. So what they do is they put it as a set and put the plus or minus here, and then list all their factors on the inside. So that way they know, hey, everything in here has a plus or a minus, but I'm not having to write that plus or minus every single time. Okay? Why am I writing the plus or minus? Because every number has to have what? All my factors have a positive and a negative. I don't know which one's going to work. Some numbers, hear me out, some numbers could work twice. You try out one, okay? Don't just get rid of it. If you're going from a lot of numbers down, try out one, then maybe try it again. Because remember, you can have a double root. You can have x plus 1, x plus 1. We've seen that happen, okay? Now, once a number doesn't work, get rid of it. It doesn't work. That's it. It's gone, okay? So let's start writing these out. Notice I start going over here. I've got, for sure, I'm always going to have 1, 2, and what? 3,
4.
Oh, sorry. Look carefully. Everything up here has to be a what? Okay, carefully. Everything has to be a fraction. So look, I can go 1 times 1, right? 1 divided by 1. That gives me 1. You want to have 1 divided by 2? Then 1 divided by what? There we go. Then I have 3 divided by 1, which is just a what?
3.
3. And then I have what?
2.
Mm-hmm. And then I have what?
3. 4.
Now what?
That's it.
That's it. Can't do anything else. Because notice I don't have anything else to divide by. There's zeros after that, and everything divided by 0 is anything to, sorry, 0 divided by anything is what? 0. So that's why you cannot add that 4 in. That can help y'all see that a little bit. People want to add it in, okay? But you don't have enough numerators to cover that denominator. Here's also, now how many numbers did I get? Don't do the positive and negative, but how many numbers did I get? 6. You want to know if you did it right? What's 3 times 2?
6.
There you go. That's how many numbers you're going to get every time. So if you have anything less than that, tell yourself, oh, I'm missing some. And go in there and look and see why. Okay? All right. Now, the rule is we got to start testing numbers. Okay? What I'm going to do first to show you is I'm going to use Descartes' rule of signs first, because I want to see what do I got coming at me. Okay? Because it might help, right? Okay, well, let's look at it. First off, I have s of x. I rewrite this as 4x to the 4th plus 16x cubed plus 11x squared minus 4x minus 3. Notice between here and here, no sign change, right? They're both positive. Okay, that's fine. Anything from here to here? How about from here to here, though? Look at that. There's one sign change. And then from here to here, nothing. You know what that tells me right now? First off, how many answers am I possibly, how many answers am I going to get? 4. But guess what I'm guaranteed? Guaranteed.
1.
1 real number. 1 positive real number. It's going to happen. Because I can't subtract 2 from that. There's only 1. So if I find 1 positive number, guess what? Every other positive number that could have been up here, I'm done. I don't have to look at those anymore. Once I found that positive. Okay. First off, that's what's cool about Descartes' rule of signs. Once I find that 1, it's like, oh, that's it. That's all she wrote. Now just worry about the negatives. So instead of dealing with 16 numbers, I'm now only dealing with, at that point, you'd be dealing with what? 8, 7, something like that. Now we got to check for the negatives. Remember with negatives, you're going to come here and change this to s of negative x. But remember what I said? If I put in negative x right here, okay? Well, negative x to the 4th power, doesn't that just turn that negative into a what? A positive. So does that change the sign of that guy at all? No. So just go in here, if you want to do it the quickie way, every odd power, Okay, yeah. On these odd powers, flip the signs. Just flip the signs of the odd powers when you rewrite it. Okay, so notice I'm going to get 4x to the fourth minus 16x cubed plus 11x squared, because it's an even power, plus 4x minus 3. Is there a sign change from here to here? Yep. Is there a sign change from here to here? 2. Sign change from here to here? Sign change from here to here? Oh yeah, look at that. Hey, what's 3 plus 1? You did it right. It has to be 4, because why? There's a power of 4 there. Okay, now, but here's the problem. I am not guaranteed 3 negative real numbers. I could get 3, couldn't I? But couldn't I also get how many? Think about it. Think about what I told you. Can't go back. Can't go higher. Because if I put 5 in, 5 plus 1 equals 6. That's not a power of 6 there. We always subtract. What can I get? Not 3, but how many? Huh? 1. Why 1? 3, 1. Complex numbers. Remember those complex numbers I told you about? Remember, they always come in pairs. So I could either have 3 negatives, but if there's 2 complex numbers in there, that doesn't tell me. So if there is complex numbers, I got to subtract 2. So then there could only be 1 negative, and I could have 1 real, 1 negative, and then a complex number at the very back end of this thing. Does that kind of make more sense now? While we do 3, 1, and then I won't have none. That's what's cool. What this does tell me now is this. Hey, once I find this guy, I'm only looking for negative zeros. Okay, that always helps out, especially when this guy gets really, really large. Okay, this one you're going to notice 1 round of synthetic and you're kind of done. Okay, watch. Are we good so far? Are you understanding what I'm doing right now? Sort of. Are you understanding what Descartes' rule tells us a little bit? Okay. Now let's go find the actual zeros. I'm going to give you the 0 right now. But what are you going to have to do? Go in there and just start playing with numbers. Okay, and yeah, they're kind of ugly. Okay. Would I jump straight into the fractions? Okay, I would probably jump. Well, I'm going to try out that 1 and I'm going to try out that 3. Okay, so let's come in here and try out one of them and notice. Here we see, I'm going to do a -1 because guess what? I know it works. Okay, so we're going to try this out. We're going to go, okay, we got 4x to the 4th. Oh, why am I doing it that way? I apologize. You only write your coefficients. I have a 4. I have a 16 and 11, a -4 and a -3. Draw my line. I love my freebie. 4 times -1 is what? Exactly, -4. 16 minus 4 gives me 12. 12 times -1 gives me what? -12. That's going to end up being what there? -1. -1 times -1 gives me a 1. -4 minus 1 gives me a -3. And then notice, -3 times a -1 gives me a what? +3, which is, what was I looking for? 0. First off, you should know it should work. You should walk into this knowing it's going to work. Why? If you plug in -1 up here, because how'd you find that -1? What did you do to find it? You had to plug it into that equation, right? And it had to equal what? 0. So that's an automatic 0. So I'm taking that automatic 0 that I know I have to take this whole polynomial, divide it, and get it down by 1 power. And then look at this whole thing and go, is this something I can factor now? Is that going to help you out? Okay, so now we're gonna rewrite. First off, if I had x minus 1, what was its factored form?
X plus 1.
Exactly. So I'm gonna write this over here, x plus 1. Come over here, notice I'm gonna have everything's dropping by a power now, right? I have 4x to the third plus 12x squared minus x minus 3. Well, I don't know about you, but that looks to me like something I could factor now. Because it's how many terms? 4 terms. So how about I come in here and go ahead and group all this. Notice on this first one, I can pull out 4x squared, and that's going to leave me with x, 12 divided by 4 is what? 3. On the back end, all I can pull out is a what?
-1.
-1, and then I get a x plus 3. Hey, so what was my other 0 up there, probably? Not 3.
-3.
-3. If I'd have tested the -3, it would have worked. There you go. Are you seeing it?
Yeah.
So then I got to rewrite everything. So notice, let's look carefully here and realize I have x plus 1, x plus 3, and then I have this 4x squared minus 1. What does that look like to you? 4x squared minus 1. Isn't that a difference of squares? So doesn't that turn into what? Come over here, and I can write x plus 1, x plus 3. Then I got to write 2 parentheses, one with a plus sign, one with a minus. Square root of 4 is 2x in both. Then put a 1 in both, and there you go. How many answers do I get? 4 answers. Well, look at this. I get x is equal to, well, that's a -1, a -3, and then I also have a what? A -1/2. And then I also have a what? What did Descartes' rule tell me? I was guaranteed what? Guaranteed. What? Look up here. I was guaranteed 1 positive. There it is. How many possible negatives could I have?
3.
3. Look up here. At most, I could have 3. Well, how many did I get? There they are right there. Are all those factors that we found earlier, are all those zeros? Well, look. Hey. There's that, and that. There they are. They're all in there. They have to be, obviously. Now, I could have just had what down here? I could have had just 1 negative, but then I would have had, if I only had 1 negative, what am I going to have? Too complex. Now, let me show you something really quick that's going to happen, and you're going to get a lot of things wrong. I will show it through an example. Let me come over here to the side real quick. Pretend. We're pretending now. Okay, we're going to use some make-believe. Let me bring this guy over here. And let's say I show you something, you do some factoring, right? And you get something that looks like this, x squared plus 1. Okay, so here it is. Here's x plus 1, here's x plus 3. Well, notice you got x is equal to -1, x is equal to -3. Are you done now, though? No. Remember, this guy isn't a difference of squares. But yet you can still treat him the same way. You can say, well, I'm still going to have this x is equal to a plus or minus what? An I, right? Okay, so watch out for that. It's going to want to see those complex answers. Okay, so just kind of be ready for those. Okay. You better with 15.3 now? A little bit? Does it look a little messy? It is. It's tedious. Okay, don't get lost. If you don't want to do Descartes' rule, you don't have to. It's not a guarantee. There, you see anywhere where it says use Descartes' rule? It doesn't. You can go in there and start testing zeros. That's all you gotta do. Okay, good news is your calculators use the fractions, so you can go in there and do the fractions pretty easy. Okay, you're gonna get some ugly numbers sometimes if you use them in your synthetic division. So I'll be honest, I tend to go with whole numbers first. Okay, but do what you want. Okay. You okay? What is our goal in 5.3? What is the reason you just learned how to do 5.3? Take a high degree polynomial and do what with it? Make it factorable by breaking it down, right? Find a zero. A zero or a root, we call it both interchangeable. Where does that cross the x-axis? Okay, by doing that, we can break the degree of the polynomial down by how many each time we do synthetic division? One. So if we have a degree of 6, man, that's hard to factor. So how about we break it down by 1? Oh, 5 still hard. Let's break it down again. Oh, 4 still hard. Let's break it down again. Each time getting a factor, not forgetting you still have a factor. Every time you get done, you have a factor. Okay? Good? Then let's learn why you take algebra. Let's jump into 5.4. The fundamental theorem of algebra. The proof of this is in your textbook. And the actual proof of this, proof meaning, hey, I'm not just saying some stuff and just wanted to hear myself talk. The proof of this can be mathematically proven to work forever. Is actually very interesting and a hard proof to understand later on because you have to take complex numbers to understand complex numbers. But they offer very good simplified proof in your textbook. Fundamental theorem of algebra states, okay, and I'm going to read it so we can be mathematically literate over it, but then I'll explain what it says very simply, okay? If P is a polynomial of a degree n, with n greater than or equal to 1, then P has at least 1 0. We know what that means, okay? That is the equation P of x, which we know P of x is defined as just any polynomial. We're just saying P of x now is a polynomial. Has at least one solution. It is important to note that the 0 of P and consequently the solution of P of x of 0 may be a non-zero complex number. Okay, look, all this says right here, n is equal to the number of solutions, and they could be real and complex. That's all it's saying. If you go back in time, and for those of you who remember this, good job. If you remember it, I probably don't believe you. I said to you in intermediate algebra, if you took me, I said the power that you have is going to be the number of the solutions you're going to get. That's the fundamental theorem of algebra. Now, I said it in a very simplified, non-mathematically correct way to you in intermediate, because when you first learned this, you had no really good concept of complex numbers. And if I had said that to you then, if I gave you this definition in intermediate algebra, you'd probably be sitting in this class right now and you'd be finding a way, is there any way out of college algebra, period? Okay? But that's all it's saying. It's saying, hey, you're going to get some answers. How many answers? It's going to match the power. That's it. You're going to get real numbers? You might. Did you just get complexes? Yeah. If I have an even power, isn't it possible to get just complexes all the way through? Yeah, think about it. 2 positive complex, 2 negative complex. If I have an odd, I'm guaranteed a real number. That's going to be nice looking at this moving forward. Okay? Linear factors theorem. Don't get hung up. The geometric of the linear factors will become more apparent here in just a little bit. Given the polynomial P of x, remember we wrote that before, you just pick an n number, you create a polynomial. All that says, if I have n is equal to 5, I would have a times x to the 5th plus x to the 4th plus, that's all that's saying. Okay, pick your n. Where n is greater than or equal to 1 and a cannot equal 0 can be factored. It's just saying, hey, can you take these guys and factor them? Yeah. Isn't that how it factors? It factors into some leading coefficient, right? With what behind it? A whole bunch of factors like x plus 1, x plus this. Well, how did you get x plus 1? Because you had a negative 1. So the formula is actually x minus, but when I put a negative in there, you get x plus 1. Okay? These are constants, possibly non-real, because could some of these end up being complex numbers? Yeah. X squared plus 1. When you solve it for 0, what does it turn into? X equals plus or minus I. In other words, an nth degree polynomial can be factored as a product of n linear factors. Do you get what that means? The power of 2 is going to have how many answers? It's going to factor into what? 2. The power of 3, you're going to get what? How many parentheses? 3. Power of 4. 4. That's all it's saying. In a very mathy term, it's saying something you've done 1,000 times. It's just now they've put it to a definition and you're like, just factor it. Okay? That's all it's saying. But now the proof is in the pudding. This is why you've been learning algebra. Because if these proofs don't hold true, you can't move forward. Interpreting the linear factors theorem. The graph of an nth degree polynomial function has at most n x-intercepts and at most n minus 1 turning points. You're gonna need to remember that for your homework. This also means that the nth degree polynomial function has at most n zeros. A power of 3, a degree 3 polynomial, how many zeros could I possibly have? 3. But how many else could I have? Real zeros. 1. Or, yeah. But I am guaranteed how many? I'm guaranteed 1 real, right? How about a 4th degree? How many reals am I guaranteed? Guaranteed. If I could have 4, could I also have 2? Could also have 0. Notice because 4 is a multiple of 2 means you might just have all complex numbers. Okay? Kind of help you out here. Odds, you're guaranteed something real. Positive degrees, you're not guaranteed. You can have all complexes. Okay? What does it mean by turning points? Where does the graph change direction? Notice this first one here. X to the 4th. How many possible zeros could I have? At most 4, but how many do I have on this one right here? Look at it carefully. A 0 is where what happens? The function does what? Well, I only crossed 2, but I have to have how many answers? Where's the other 2? They're complex, they're not graphic. Okay, but notice it only has 1 turning point. This thing is, I'm just going to say that it's going down. I don't know that for a fact, but we're going to say it's going down. But then what happens right here? It turns and it goes what? Up. So it can have at most n minus 1 turning points. So I can't have 4 turning points if I have a degree of 4. I can only have at most how many? 3 turning points. Okay. Let me show you why real quick. Well, look at this right here. If I showed you a 4th degree, let's just say it looked like this. 1, 2, 3, 4. Well, how many zeros do I have? 1, 2, 3, 4. How many turning points do I have? Do I want to have 1 here? Do I have 1 here? Do I want to have 1 here? Well, it's 4 minus 1.
3.
N minus 1 turning points. That's all that's saying. I can't have 4 turning points because that means this guy did this. He turned, went back down, and now all of a sudden a 4th degree polynomial has 5 answers. Can that happen? No. That's why they're saying n minus 1. Now notice the other one, the cubic polynomial has how many answers? 3 with how many turning points? Can you see it now? Okay. You know what's better about this too, though? You're gonna love it. I love it. Gives me goosebumps. Because I'm a nerd. Okay? You're learning how to graph. Do you not realize that? You're learning how to just see graphs. Okay, in your head before you can graph it. Okay? Watch what the geometric is behind this. We're gonna learn about multiplicities. If the linear factor x minus c, remember when you see x minus c, that's literally just saying what? X minus 1, x plus 2, whatever, right? When you factor something, can we all agree sometimes when we have factored, sometimes we could get x plus 1 squared? Can you get that? Think about it. Hear me out. Everybody's forgetting it. I get it. I'd forget it too. What if I gave you x squared plus 2x plus 1 all equal to 0? Well, how would you factor that, guy? Wouldn't it just factor into what? I've got a pretty coefficient of 1. That's going to give me x in both of them. Positive sign says same signs. Both of them are going to be positive. The only factors of 1 are what? What did I just get? X plus 1, or what? X plus 1 squared. You see what I just did there? So can I get an x minus c and have it be greater than a power of 1? Hopefully I just proved that to you. Could I get x plus 1, x plus 1, x plus 1? Yeah, all I need is how many, what would have to be the leading, what would have to be the degree? 3. Think about it. To get x plus 1, x plus 1, x plus 1, I'd have to have a degree of 3 at that point, right? To get x plus 1 4 times, I'd have to have a degree of what? 4. Okay, are you good now? Proof is in the pudding now? Okay. Watch this. Here's what's cool. I'm serious, it's kind of neat. Because some of your homework's gonna say, hey, where is the graph going across the x-axis? Well, look at what's happening here. When you have an odd power, well, I'll be writing that down. It's always going to cross the x-axis. Always. Notice it did, right? You know how else I knew that? Did helping remember my graphs kind of help out as well? So notice, x minus 1, well, where does it go across the x-axis? What's my 0 there? Yeah, it's at 1. Now, don't get fooled by that graph saying, well, it looks like it's 1 for a while. It's not. It's only 1 that long. It's just getting so infinitely close, and then at one point it touches it, and then it starts going and doing its thing again. Okay? That's called it going across. Now, the other way, if you have an even power, it does a bounce. It hits the x and bounces off. It doesn't cross it, you only get 1 x. So where is this going to equal? What's my x value? Yeah, -2. It's going to come down, 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 hit it, and then go up again. That's all that's going to happen. Kind of, we call this multiplicity. Okay, notice all you have there on that f of x is equal to x minus 1 to the cube. You have x minus 1, x minus 1, x minus 1. Well, you don't get an answer if x equals 1, 1, 1. You just get x equals 1. Okay, same thing with 4. You're going to have, what is it, a -2. Well, you don't get -2 4 times. You just get a -2 1 time. Okay, but did you notice the difference between that and a quadratic? What happens with a quadratic? It kind of does what? It's a little bit skinnier, isn't it? Quadratic actually looks like a ball just kind of just doing this little motion. This one looks like it kind of hits it and flattens out a little bit, right? Remember that's kind of how you remembered your graphs a little bit? Remember I showed you those back in 3, 4? You know, x to the power 2 looks like a parabola. X to the power 4, a little bit more flattened out. X to the power 6, a little bit more flattened out. What do you see happening? The larger the power get, what happens?
That one.
Yeah, it flattens out longer and longer and longer. Doesn't mean it equals that everywhere. It only equals it at one spot, but still. Okay. Well, that's good. You know, it's nice about that. And I'll give you the real quick here, just so you have these definitions here. These are in your deal. Okay. Notice the very bottom part. If K is greater than 1, the graph P will flatten out. Well, yeah, that makes sense. X cubed looks like this, doesn't it? What would x to the power of fifth look like? A little bit more flattened out. It's a 0, right? What would x to the power of 7? A little bit more flattened out at 0. And you just kind of keep flattening out and flattening out and flattening out. That's all you're doing. Now, what's going to happen later on in your homework? It's going to say, hey, what's the degree of this polynomial? Well, add all your x's together, right? And go, okay, I've got this many, this many. I've got 7. There's my degree. What's your x-intercept? Make everything equal to 0. And that gives your x-intercept. Can I help you out a little bit? I have to stop. Is anybody lost right now? Completely lost. You're like, I have no idea what's happening right now. Or are you okay right now? Sort of. Like you're okay enough to go, man, I'm in the pool. I'm not in the deep end yet, but with some practice and doing some homework examples, I'll get this figured out. Okay. But does the concept make a sense a little bit? Are you okay? Okay. Good. Conjugate roots theorem. Probably the harder part of this lesson. Not harder, the more messy. Okay. How many complex numbers am I guaranteed? If I get a complex number, how many do I have to have? 2. Both positive? One's going to be what? Yeah, one's going to be positive. You're always going to get positive and negative. This is why this lesson kind of reaches backwards, and I kind of start telling you here when it's weird. They don't really tell you here. I really kind of wish sometimes that I would show you the theorem first and then show you 5.3. I kind of really wish they would turn these lessons around a little bit. Okay. Look here. Conjugate roots theorem. Let P of x equal that whole big polynomial again with only real coefficients. If the complex number a plus bi is a 0 of P, a complex number is still a 0. It's just it can't be what? You can't graph it. It's there, isn't it? Because we do solve for it. Well, then notice what it says here. Then so is the number a minus ba, which is, remember to use that word, in fact, the conjugate. A plus b, a minus b, okay, with the I. In terms of linear factors P, this means that if x minus a plus bi is a factor of P, then so is x minus a minus bi. Okay. Those are just 2 factors of it. So look at this example. Given that 4 minus 3 is a 0 of the polynomial here. That means after this thing's completely factored, this guy ends up being one of your zeros. Okay? Well, then what do? Look at it carefully. And I'm going to work it out. I'm going to work it out pretty quickly because I do want to get to some of your homework examples. We'll do a couple more tomorrow, but then we got to finish up with 5.5. Okay? Don't forget, I haven't moved it yet. 6.1 and all that stuff is not due on Monday now. I'm moving it to Friday of next week. And to be honest, I may move it to the following Monday. All your chapter 6 stuff, so that we've got all week long to study everything in chapter 6. And then you've got the weekend to kind of finish up the homework. I know that kind of bunches everything up, but, and then the following week after that, Monday and Tuesday, we'll just do review for your final. Okay. So looking at this one right here, very carefully, this is what it's saying. Since 4 minus 3 is a 0, what else has to be a 0? What does the theorem say? If I have a 4 minus, I have to have a 4 plus. Okay. So realizing that both of these are factors, I can write it like this. X minus 4 minus 3i x minus 4 plus 3i. Right, those are just factors, right? I'm saying the x minus because look, remember x minus c is my formula for this, okay? I just plugged everything into the formula. I'm going to do this next part pretty quickly, okay? Matter of fact, I'm going to skip a step. You can go in and do the math yourself or look at my notes and see how I did the math, okay? It's just a lot of foiling, okay? Notice I'm going to go ahead and take that negative and distribute it into there so everything can get switched around. And I'm going to get x minus 4 plus 3i. X minus 4 minus 3i. Like I said, for sake of time, I'm not going to be able to show you. All I'm going to do is go, hey, x times negative 4, x times here. Write it down, right? We're foiling. It's just a lot. When I do all that, let me just kind of do a dot here. You're going to get x squared minus 8x plus 25. Okay. Hear me out here. How many answers am I supposed to have? How many zeros am I supposed to have? 4. How many do I have right now? I only have 2. But here's a quadratic, right? Here's also a quadratic. Just because you learn synthetic division doesn't mean you have what? Long division. Remember that long division I taught y'all? Can't use synthetic on this one because this one isn't of the form x minus c. Okay, so this one right here, I'm going to take this whole guy here, okay, divide my main f of x by that guy right there. So look what I'm going to do. Once again, I take the whole polynomial here. I've got x to the 4th minus 8x cubed. What do I have to do real fast? What are you going to see me do? Am I missing a power 2?
Yes.
What do I have to add there?
0.
Add a 0 because I got to have that placeholder, don't I? And then I'm going to have to add that plus 200x minus 625. I'm dividing this whole thing here by x squared minus 8x plus 25. Take this x to the 4th, divide it by x squared, and I'm going to get x squared. I'll put it back right here. I'm going to FOIL all that, right? Or I'm going to distribute that x squared back into my original dividend, right? Sorry, my divisor. When I do that, I get x squared minus 8x plus 25. But remember, I put this negative on the outside, so what's going to happen to every single term in there? Remember, I'm subtracting. Oh, sorry, and that is x to the 4th here. I apologize. 4th, 3, and don't forget you got an x to the power 2 here, so I apologize. Did that too quickly. Everything here is going to change the sign, right? So notice here, I'm going to have a negative here, a positive here. That's going negative. That reduces out. Hey, looks like that's nice. That reduces out as well, doesn't it? Okay, and so I'm going to be left with negative 25. X squared. I'll bring down everything else. Plus 200x minus 625. And then we do the same thing again, don't we? Negative 25x squared divided by x squared is just going to give me what? Negative 25. So that negative 25 will go right over here. Put everything back together, and I'm going to get a negative 25x squared plus 200x minus 625. But I'll go ahead and throw this out here, which is going to change all my signs, which hopefully you can look at that. When you change all the signs, what's going to happen to everything on the bottom? Yeah, that all reduces out. Okay. And so I have a remainder of 0. And so notice what just happened. Look at what I have. I have x squared minus 25. What does that mean? That means 2 of my factors are what? Well, don't I have a factor that says I have a 4 minus 3i and I also have a 4 plus 3i? But notice what else I have here. I have x is equal to, hey, x squared minus 25. Then I also have what? X minus 4 plus 3i and x minus 4 minus 3i. So that guy has now been factored. If I solve for all of those, what would I get? Notice I would get 4 answers. X is equal to positive or negative 5. There's 2 real answers, right? And then over here, get everything to the other side, and you would just get your positive, what would you get? X is equal to 4 plus or minus 3i. Make sense? You got how many answers? 4. How many were you supposed to get? 4. Why did it not give it to us in the beginning? Because it's literally proof of concept. It's saying, hey, if I give you one complex number, guess what you got to have? You better have another one. Then you can take these guys, fold them together. You're going to come back to a polynomial. You have to, because that's like saying 5 times 5 is 25. And then how many times will that go into 100? Well, you're going to get another factor out of that, aren't you? Okay. That's how that works. Okay. Let's see here, 38. I can do this one pretty quick. Let's do this first example. Okay. Very, very quickly, just so you kind of know how to do it. First off, find the degree and the y-intercept. First off, the degree, hey, add your powers. Yeah, look, you got 2 here. How many there? 3. Oh, almost 5. How many got right here?
4.
2 plus 3 plus 1 is how many? It's a 6th degree. Look at your powers. 2 plus 3 is 5. There's always a 1. Okay? Now, what's your y-intercept? To have a y-intercept, what does x have to be? 0. So plug in a 0 here. So f of 0 is, well, 0 plus 4 squared, 0 minus 2 to the third, and then 0 minus 3. If you'll permit me, I'm going to go ahead and give you the answer to this. You should know how to work it on your calculator very quickly. Be careful, you're going to get a blue bar, or it's going to say, you're giving this to me in the wrong form. Because a y-intercept is always of the form what? The point. So how would I write that?
Comma.
0, comma, my number here, which is 384. 0, comma, 380. Okay. Now, notice this part. Watch carefully. And I don't show this to you on here, but the moment you click a 1, 2, 3, or 4, you're going to get boxes underneath. And it's going to say, okay, give me the points. If you put 0, obviously, nothing. But what it's asking for here is, look at it. Select the number of x-intercepts. Where does it cross the x-axis? How many times is it going to cross the x-axis? Every time you see a positive, every time you see an odd number, that's one crossing. Do I have a power 3 here? It's going to cross there. Do I have a power 1 there? It's going to turn and cross again. So I'm going to get 2 because I have a power 3 here. There's a crossing. Here's a power 1. There's another cross. What's going to happen right here at the power 2? What would happen? It would bounce. Remember, that's where it doesn't go across. It bounces because it's an even number. So once you do that, you're literally going to come here and it's going to say, hey, well, where is it going across at? Where is it happening? So you come in here and you're going to have 2 coordinate points. Well, at one of them is x minus 2. Well, isn't that going to be just at 2, comma 0? Where's my next one?
3.
Very good. Do you get it? Odd numbers, you're going to have an x-intercept. Okay, even numbers, because it bounces. And then the last question, then we'll call it a day, and I'll finish up a few more of your examples tomorrow before we finish up with 5-5. Okay, but look at this right here. Find the zeros in which f flattens out. Flattens out. Remember, as it gets larger, realize what it says. Anything where k is greater than or equal to 2, the graph is going to start to flatten out. So where am I going to flatten out? How many places am I going to flatten out?
2.
2. Where? Here and here, right? Wouldn't it start to flatten out there? Even though it's going across, think of it this way. Just because it's going across does that not mean it can't do this? Come up, flatten out for a little bit, and then go back up again. Right? Or if it's a parabola, can it come down, flatten for a little bit, and then go back up again? That's all it's asking. So if it's going to happen at 2 places, where does that happen at? Once again, you're going to have 2 coordinate points. Well, what are they going to be? Exactly, -4 and 0, and where else?
2 and 0.
And 2 and 0. And that is how those are done. Tomorrow, I'll go over a couple of more questions for you. Looking here, like we've got this one right here. We got a few here. This is a 4-part down here. Probably won't be able to get to it tomorrow, but notice it's what we just did all the way through. Except on this one, they do a 1 to 4. They say, hey, factor it first, which means you got to do what?
Division.
Go back to 5-3. Find all your zeros. Find out which one's what. Factor it, and then start finding everything from there. Okay. Now the thing is about factoring that one, you could end up with where you get a 1, and then you get another 1, and you get x plus 1 twice. So therefore, you have a power of 2. Okay. So, all right, guys. Tomorrow we'll finish up 5-5, and then remember, no class on Thursday.